We physicists have been waiting a century, since about 1916, for this renowned physicist, Dr. Kaku, who was a pioneer in the field of hypothetical physical science. His life's work has been to unravel the universe's deepest intimate secrets. He is currently on a quest to question and potentially reform the fundamental laws that control our life. Dr. Kaku, who is widely acknowledged as one of the most notable logical figures of our day, strongly suggests that the planet Earth might be contained within the boundaries of a black hole. Just imagine the profound ramifications. Our entire perception of life encapsulated under the immense gravitational pull of these priceless riddles. However, what is a black hole exactly, and how could it form? Join us as we explore the amazing possibilities concealed beneath these opulent quirks as we go deeper into this captivating trip. We will examine continuing observations made by the James Webb Space Telescope, which may change our understanding of the origin of the universe. Leading scientists have shown that black holes are enormous, unpredictable marvels rather than just empty spaces in space. Even light is unable to escape these massive convergences of matter, which are compressed into incredibly small distances due to an incredible gravitational pull. Despite their invisibility, they leave a noticeable trace due to the substantial impact they have on the surrounding material. Quasars, the astounding constituents of the cosmos, are a few black holes encircled by whirling circles of gas and dust that emit enormous amounts of radiation. However, how do these fascinating quirks come about? Scholars have proposed two types of black holes: huge black holes that reside at the center of galaxies like our own Milky Way, and brilliantly heavenly black holes formed by the collapse of immense stars. Though the precise processes of development are unknown, speculations include everything from celestial disintegration to the devouring of nearby stars over extremely long ages to the mergers of smaller black holes. New findings from the James Webb Space Telescope cast doubt on long-held beliefs, particularly in regards to the universe's beginnings. Recognized for his practical insights, Dr. Kaku highlights the amazing discoveries made by the telescope, such as the discovery of worlds several times larger than the Milky Way and galaxies discovered only a few billion years after the Big Bang. This finding poses a serious threat to existing ideas because such massive galaxies shouldn't have formed at such a young age. In light of these remarkable findings, Dr. Kaku emphasizes the necessity to reconsider and perhaps completely rewrite our knowledge of the universe's origins. These billion-star galaxies, which emerged during the early phases of the cosmos, provide significant concerns regarding cosmic evolution and the underlying principles that control our existence. Recent discoveries cast doubt on existing theories by suggesting a faster and earlier development timeframe for galaxy formation than previously believed. New ideas in galaxy formation theories, or fresh insights from physics, may be needed to solve this intriguing puzzle. As Dr. Kaku has appropriately termed them, the revolutionary finding of these universe breakers underscores the power of the James Webb Space Telescope to offer a new angle on the early history of the universe, challenging preconceived notions and promoting exploration of uncharted space. Through the analysis of JWST photos from July 2022, researchers from Swinburne University of Technology in Melbourne, Australia, under the direction of EVOL Throw, achieved a significant breakthrough. 6 galaxies with exceptional brilliance and a reddish hue that were previously invisible to other telescopes were visible in these photos, which only covered a small portion of the sky. They calculated the universe's distance from Earth using photometric redshift estimates, and the results showed remarkably high redshift values ranging from 9.5 to 11.5. This implies that these galaxies' light began to shine more than 700 million years after the Great Bang. Subsequent analysis showed that these galaxies had very huge stellar masses that rival or exceed our Milky Ways, with masses ranging from 10 to 100 times that of our Sun. These results suggest a quick conversion of gas into stars, which is at odds with accepted notions of slow galaxy creation. As these galaxies contained more mass than was typical for their individual regions of space, contradictions with cosmological models based on investigations of the cosmic microwave background also emerged. These galaxies' ancient red star populations sparked concerns regarding chemical enrichment in early environments and star formation. In order to reconcile these discrepancies, scientists explored various theories, including as the idea that these objects might not be galaxies at all but rather quasars or other active galactic nuclei driven by extremely enormous black holes at their centers. These findings demonstrate the intricacy of the early universe and the necessity of more research and improvement of our observations. But issues are raised by the lack of distinct cosmic marks that one would expect from active galactic nuclei in these objects. Matter creation and piling onto extremely big black holes usually take time, which makes this odd at such high redshifts. There's also a chance that the theories and models that were applied to analyze the observations contained errors that raised questions about the evolutionary history of these galaxies. To solve the puzzle surrounding these remarkable galaxies and shed light on the mechanisms underlying their origin and evolution, more investigation and study are required. These processes could include the rapid formation of huge galaxies without the need for mergers or slow buildup. However, instead of being typical of the universe at that time, these galaxies might be oddities that emerged in uncommon locations or under unusual conditions. These discrepancies might put our knowledge of cosmology or physics to the test by pointing to new linkages or events that go beyond the purview of existing models. According to Dr. Kaku's conjectures, the early universe's volume and matter distribution may have been influenced by events like the destruction of dark matter or primordial density fluctuations, which might have led to variances in mass and faster expansion in some areas. Evidence for other dimensions or forces, as those implied by modified gravity or string theory, may also have an impact on our comprehension of the fundamental laws of the universe. Even though these are just hypothetical scenarios, they highlight the necessity of greater research and testing in the coming years using larger datasets and more sophisticated models. With a variety of equipment that may perform in-depth studies, the James Webb Space Telescope is anticipated to yield further details in the future about these intriguing galaxies and their implications for cosmology and physics. In the meantime, globular clusters, ancient collections that contain thousands of stars in a small area, have been the subject of fascinating new discoveries made possible by studies made with the James Webb Space Telescope. According to Webb's findings, these clusters contain a large abundance of nitrogen and stars that are remarkably brilliant, indicating the presence of massive stars. These discoveries open up new options for studying star dynamics and evolution by providing hints about the origin and development of these mysterious groupings. Dr. Kaku provides a different interpretation for later findings in the midst of these discoveries, speculating that black holes rather than young galaxies might have been detected by the JWST. According to this notion, which contradicts accepted theories of universe formation, these objects might be huge black holes that formed in the aftermath of creation. Such a concept pushes the frontiers of our possible universe interpretation, suggesting the emergence of new laws of physics within these enigmatic cosmic structures. When the universe is taken into further consideration, a related theory puts out that the universe might actually be a big black hole that formed when a massive black hole collapsed, creating a much larger cosmos inside the black hole's event horizon. There is so much gravity here that nothing can possibly escape. There is a singularity, a point of infinite density and curvature, when space-time becomes distorted. There is a chance among some experts that there is another event horizon inside the black hole that extends to a cosmos beyond our current comprehension. This fascinating idea raises the possibility that there are several universes contained within other black holes by implying that our universe is housed inside a black hole that is nested inside another universe. Although this theory is supported by theoretical models, no research or observational data have yet to corroborate it. Still, this theory presents a convincing picture of our enormous ancestry. A persuasive hypothesis suggests that the universe was born from a dense state of matter and energy approximately 13.8 billion years ago, focusing on the events leading up to the Big Bang. It does not, however, address the question of what preceded this initial situation or what caused it. Dr. Kaku is among the scientists who are dissatisfied with this explanation and are searching for a deeper cause for the universe's birth. An interesting hypothesis that provides a fascinating perspective on our huge beginnings holds that our universe originated from a black hole in another universe. In 1973, Russian physicist Andrei Linda put up this theory, which was further expanded upon by scientists like Lee Smolin, Nikolai Kolesnikov, and Stephen S. Hawking. This theory suggests that there are innumerable universes, each with its own unique set of physical rules within an enormous space known as the multiverse, of which our world may be just one. Consider these worlds as distinct entities, each possessing unique laws and features. A few of them might even be home to remarkable phenomena like black holes, which have the ability to create entirely new universes. How is it possible? Think of a black hole as a structure that exists within the general theory of relativity, which explains the structure of existence. A singularity, or parent abyss, is formed when gravity inside a black hole is so intense that it distorts reality. Some physicists contend that these singularities are only mathematical oddities rather than real entities. They propose that quantum effects become relevant at the edge of general relativity, preventing singularities from occurring within black holes and creating new, distinct areas of space-time. These new regions of space and time may represent new universes with completely distinct rules of physics, isolated from their parent universes by event horizons, the limits beyond which nothing can exist or interact. This amazing idea imagines, amid the confusing depths of a black hole, a cosmic divide between universes, each with its own unique attributes. It's possible that new worlds are forming, which would push the boundaries of our knowledge and show us the countless possibilities that exist inside the enormous multiverse. There is another theory that these recently identified areas of space-time could be tunnels or shortcuts caused by wormholes. Changes the structure of space-time, providing a fascinating new avenue for investigation into the fields of theoretical physics and cosmology. Speculative solutions to Einstein's general relativity equations, known as wormholes, present an intriguing possibility in which the two ends of the wormhole connect to different universes. The two ends would be outside the event horizon of a young black hole and the other inside a black hole, more precisely inside its event horizon. This idea is intriguing because it suggests that matter and energy falling into a black hole in one universe could emerge as a white hole in another. A white hole functions as an area where nothing can enter but everything can exit, in contrast to a black hole, from which nothing can escape. It serves as the starting point for a new universe by supplying the elements of matter, energy, space-time, and physical rules. There may be an infinite chain or network of universes within universes if this process continued indefinitely. Within this vast cosmic tapestry, every universe has a distinct history, evolution, structure, composition, and ultimate destiny. This theory provides a convincing account of the origins, existence, and fate of our universe. Additionally, it offers possible explanations for a number of cosmological mysteries, including the reasons behind the lower entropy of our universe, precisely calibrated physical constants, dark energy, dark matter, cosmic homogeneity, large-scale structure, primordial gravitational waves, cosmic microwave background radiation, quantum fluctuations, and quantum entanglement. Nevertheless, there are a number of problems and criticisms with this theory. It is quite theoretical, untestable, and unfinished despite its allure. Its detractors claim that it has ad hoc explanations, contradictions, circular thinking, and inconsistencies. Its exploration of speculative and human-centered fields further complicates the task of establishing its scientific legitimacy. Although this theory offers an engrossing story about the nature and existence of our world, it faces major challenges that cast doubt on its validity as science and applicability in real life. The possible discovery of primordial black holes is a fascinating field of study as we continue to delve into the depths of our universe. These hypothetical objects are thought to have originated soon after the Big Bang in the early cosmos and may have been important for the evolution of the universe. Some of the unanswered mysteries regarding the origin of the universe and the dispersion of dark matter may be clarified by their existence. The estimated masses of primordial black holes vary depending on the circumstances of the early cosmos, ranging from microscopic to stellar-sized. Since their gravitational pull would affect how galaxies develop and behave, if they exist, they could offer vital new information about the nature of dark matter. Furthermore, its possible discovery could provide fresh insights into quantum gravity and the connection between general relativity and quantum mechanics, as well as validate a number of theoretical predictions. Numerous gravitational wave events have already been identified by observatories like LIGO and Virgo, providing a new means of studying the cosmos. These discoveries support certain aspects of Einstein's general theory of relativity and offer a fresh perspective on the dynamics of neutron stars and black holes, illuminating events that are otherwise unobservable with conventional telescopes.